All right, are there any questions based on what we covered last time? So last time we were looking at the ratio analysis of CDNA microarrays. And I sent you the paper and some explanatory material last week. All right, I'm going to discuss that today and probably on Wednesday. Okay, but let's just finish these slides and I will go to that paper. So any questions so far? I will show you how we come up with this formula. Okay, I will cover a little bit of maximum likelihood estimation and how you get this estimate C hat, right, from the housekeeping genes on the microarray. Okay. Because on the housekeeping genes, your expectation is that the values for those ratios should be 1, right? Because the housekeeping gene is just doing the regular function. So the values shouldn't be different between, let's say, the test sample and the sample that you're interested in. Okay. So no questions so far? Okay. Now, you can go ahead and use housekeeping genes to calculate the value of C, right, using the formula that I showed you a moment ago, all right? Otherwise, you can use some other techniques. And again, these are rules of thumb. So for a microarray that is derived from 2 identical mRNA samples, co-hybridized on one slide, that means even the green and the red, okay, it's really the same sample, okay, you've broken it up into 2 parts, you label with green and with red, right? So your expectation is that at every spot, you're going to have a ratio of 1, right? Because barring experimental error and other sources of variation, everything should be the same, right? So for a microarray derived from 2 identical mRNA samples co-hybridized on one slide, it's called a self-self experiment. The parameter C provides the variation of the assay, right? And this parameter C is the coefficient of variation. However, for any experiment to guarantee the null hypothesis, and remember the derivation of that formula, right? Or these experiments are being carried out under the null hypothesis. That is, the red and the green have exactly the same intensity, right? That's what the assumption that you're making. So one alternative might be to duplicate some or all clones where the same expression ratio is expected, right? So maybe for gene number 1, so instead of using identical samples and trying to do it this way, okay, to get the variation of the assay, one alternative might be to duplicate some or all of the genes where you expect the same expression ratio, right? But if they are different, then that is a cause for alarm, right? It should not be different, it should be same, right? That means that is the variation between the different spots. So for the ratio T of expression ratios, right, it can be shown. So you're now taking a ratio of expression ratios, right? So it can be shown that the variance of that, of the logarithm of that, and again, you'll probably have to look at some of the papers to see that is equal to 4 times C squared. So you can measure this quantity, right, and from this you can get the value of C, right? So for any given experiment with some duplicated clones, you can easily calculate the sigma square log T, that is the variance, all right, of the log of this ratio of expression ratios. That could be calculated, and along with it the coefficient of variation of the assay could be calculated, right? Now in practical applications, see the red and the green channels, all right, the intensities may not be the same, okay? Maybe the laser in the red channel is more intense than the green channel. In that case, 1 would not be the value around which you're going to test things, okay? It might be something else, okay? If the green channel is twice as intense as the red channel, then the green by red ratio normally is going to be 2, right? So you would test it around 2. So in practical applications, a constant amplification gain M may apply to one signal channel, in which case the null hypothesis will become like the mean of the red will be M times the mean of the green, right? And under this uncalibrated signal detection setting, the ratio density can be modified as follows, okay? And this is nothing like, as an undergraduate when you took some basic course on probability, all right, you basically went ahead and calculated the density function, all right, for functions of a random variable, all right? So if you multiply a random variable by A, all right, this is the formula for the density function, right? What happens? So if you multiply it by M, you'll get 1 over M and then F of the variable over M, all right? Same density function. And I will go through this again. For people who may have forgotten everything, all right, or who don't like probabilities, I will go through that. That's there in that explanatory material. Now to decide whether expression levels of a gene from 2 samples are significantly different, right? We would like to find a confidence interval, because you cannot just go and check, okay, is the ratio 1 or not? It will not be 1, okay? It might be 1.01, 1.05, it might be 1.09, all right? And you would have to have an interval around it, all right? So that you can say that it is significantly different from 1, okay? So for that you need the probability density function. So you need to find a confidence interval such that within the confidence interval, the null hypothesis cannot be rejected, right? You will say that the two populations have the same mean, right? The expression ratio, TK, which is the ratio of the red intensity to the green intensity, is not significantly deviated from 1 if the ratio is within the confidence interval, right? And the confidence interval, how can you calculate that? You can evaluate it by integrating the ratio density function. And again, these are things that you probably know from probability and statistics, right? When you do hypothesis testing and all this overlap and all that, you integrate out the area. Again, not to be alarmed, right? If you don't know this stuff, I've given some explanatory material. Okay, I'm going to go over that. That will explain, right? If you've forgotten all this stuff, right? In fact, last time I taught this course, it was a combined undergrad class, and I had like 1 or 2 undergraduate students, they got really upset, right, that they needed to know this material because I never said that, you need to have 303 or something like that, right? Because the probability and statistics stuff, because there's some classification, right, some Bayesian classification, some clustering and all that. And I thought it was simple enough, the brightest students, of course, picked it up. But for the others who had poor background in probability, they told me next time you have to mention that that's a prerequisite. Now you're all grad students here, so I don't think I need to worry about that. Now, since the confidence interval is going to be determined by that parameter C from the density function, one can either use the parameter derived from preselected housekeeping genes or a set of duplicated genes if they are available in the array. So if you're using housekeeping genes, all right, so the confidence interval that you determine from housekeeping genes will contain some level of variation from the fluctuation of the biological system that also affects the housekeeping genes, right? Because from one experiment to the other, it's a different system, right? So it might, in theory, yeah, the housekeeping genes shouldn't be affected, but there might be some effect, okay? So you will observe some confounding factors. Whereas on the other hand, if you're having, duplicated genes, not housekeeping genes, or genes that respond, but you're duplicating them at 2 different locations, right? So the expectation is that you should get the same response, right? But it might be different because of spot-to-spot variation on the microarray, right? So that's what this says. So, while the latter, that is if you use duplicated genes, will contain no variation of biological fluctuation, right? Because this is the same gene that has been duplicated, but it'll contain probably some variations that will come from variation between different spots on the microarray, right? Now, spot variation is not avoidable if one wishes to repeat the experiment, right? Every time you're not going to get it exactly at the same spot, okay? Things will change. Now, the confidence interval that is derived from the duplicated genes is termed as the confidence interval of the assay. Now, the constant, we have made an assumption, that all the spots on the assay, the signals, they have the same coefficient of variation, which means the same ratio of the mean to the standard deviation, right? We made that assumption. The paper gives you some biological justification for that, right? So the constant CV condition permits all ratios satisfying the null hypothesis to be pooled to estimate the parameter, right? And I discussed that earlier, right? Because once you make this assumption, and I will show you the derivation, okay? The density function that you will get at each spot, it will not have the, k as a parameter, right? The spot, so you'll get the same density function at each and every spot, okay? Which means you can pool the data together to get your estimate of C. Now, however, so this is the assumption that is made, the constant coefficient of variation assumption. However, studies indicate that the coefficient of variation varies with the expression intensities. So if the genes are expressed at a good level, expressed pretty strongly, right, then it's fine. But if it is, very weak, right, then you may have problems with this assumption. And then there are fixes that people have proposed in the literature, but we are not going to get into them. So the constant CV condition is made under the assumption that the red and green are the RK and GK are the expression levels detected from 2 fluorescent channels. The latter assumption is based on the assumption that image processing will successfully extract the true signal, right? Now this proves to be quite accurate for strong signals, but problems arise when the signal is weak in comparison to the background, right? So if you have a low signal to noise ratio, then there can be trouble. Now the following figure, so that's on the next slide, right? This shows, so this is the intensity, right? For one of the colors, this is psi 3 and psi 5. One of them is red, the other one is green. Okay, they call these dyes psi 3 and psi 5. So you can see that as you're going towards the lower intensity, all right, there's a lot of scattering around this. Okay, so a lot of variation is going to creep in. So So the figure shows how in many real-world situations the weaker expression signals at the lower left corner of the scatter plot produce a large spread of gene placement. Right? Even with image processing, the actual expression intensity measurement is of this form. The actual measured intensity is basically the signal, right? Let's say we're looking at the red channel at the kth spot, right? The actual measured red intensity is the actual red signal plus the background associated with the red, right? Minus the mean of the background, right? Associated with the red, right? Where SRK is the expression intensity measurement of gene K, BRK is the fluorescent background level, and mu BRK is the mean background level, right? Now the problem is, see this guy, all right, if you're looking at this signal, all right, is the actual expression intensity. This will satisfy the constant of variation, constant coefficient of variation requirement. Okay, but however, you're going to work with this signal. Okay, RK and GK. And these will in general not satisfy that assumption. Right. So that's the problem. So the measurable quantities here are signal with the background, right? That is the red signal plus its associated background at the kth spot, right? And also the surrounding background. The null hypothesis of interest is that the mean of this signal, right, at the kth spot, red signal at the kth spot is the same as the mean of the green signal at the kth spot, right? Now if you take the expectation, right, we had this expression for RK, right? If you look 2 slides back, all right, you have this expression for RK. This is a random quantity, right? So if you take the expectation, right, you'll get expectation of this guy plus the expectation of the background, right? And then that'll cancel out with that mean background that you're subtracting, right? So this will cancel out. So you will get that the mean of this guy will be the mean of the measured signal will be the same as the mean of the signal that you're actually interested in tracking, right? So that's a good thing, but you cannot say the same thing about the variance, right? So taking the expectation in that earlier equation yields the mean of the red is the expected value of the signal that is the actual signal that is measured at the red signal that is measured at the kth spot. So you do the expectation operator and you get this is actually the mean of the original signal, right? So since the mean of, similarly you can show that the mean of the mean of the green signal measured at the kth spot will be the same as the actual signal that you're interested in measuring at the kth spot, right? So the hypothesis test is still the one with which we are concerned, right? That is equality of means, right? And we can still apply the test statistic, the ratio statistic TK, right? There is, however, a major difference. The assumption of a constant coefficient of variation applies to those original signals, SRK and SGK, not to these measured signals RK and GK, right? And therefore, the density function that you derived under a constant coefficient of variation assumption is not applicable anymore, right? So this was basically image analysis of cDNA microarray images, where in the microarray, right, you're going to basically put the complement of the different genes at each spot, right? So you're going to have complementary DNA. As I mentioned last time, another way to produce a microarray is to have synthetic DNA, all right, immobilized at different spots, right, on this microarray. And you know, these will typically not be very long, right? Maybe 25 nucleotides or something like that, right? So you have a gene of interest, right? Then you take small pieces, right? And then put in like small probes that are complementary to different portions of the messenger RNA that you're going to be interested in, right? So that's the method that uses what are called synthetic oligonucleotide arrays, right? So a different approach than that of immobilizing cDNA or complementary DNA strands from particular messenger RNA transcripts onto a surface is to fabricate synthetic polynucleotides onto the surface. For the popular Affymetrix chip, photolithography and solid phase DNA synthesis are used to synthesize desired polynucleotide probes at specified coordinates on the slide, right? So since these synthetic probes are much shorter than the genes, okay, these might be like 25 base pairs or something like that, okay? Gene will be like thousands, okay, kilo base pairs. So they must be designed in such a way that their collective action. So for one gene, you will have many different probes, okay? And then you'll have to weight the responses you get at the different probes to come up with the intensity levels for that gene, all right? So here we are discussing probes that consist of only 25 bases or 25 mers, and a single 25 mer may pair with a large number of messenger RNAs, okay? It may not even be one gene, okay? It might pair with a lot of other genes. So there is possibility of a lot of cross hybridization too, right? So you have to be innovative, right, and try and think of techniques that you can use to cancel out, the effects of possible cross hybridization. Right? So for each messenger RNA of interest, there is a set of non-overlapping or almost non-overlapping 25 mer oligonucleotides. That means synthetic nucleotides with 25 bases, right, in them, to provide sequence-specific detection that can lead to accurate abundance measurement at the next stage of the process. The probes must be designed so that the final measurement for a particular gene is not unduly affected by the fact that the short probe will hybridize to transcripts from other genes also and other kinds of RNA in the sample. Right? So you'll be picking up a lot of other stuff too because with these short probes. So the basic approach is to have, for each messenger RNA to be detected, a probe set for which different probes will hybridize to different regions of the messenger RNA. Right? And in this way, the measurement of a specific messenger RNA is obtained via averaging across a collection of probes, thereby mitigating the effects of noise, outliers, and cross-hybridization. Right? And these companies that make these chips, like Affymetrix chip, right, they have their own proprietary, algorithm for coming up with the expression intensity of the desired gene based on those measurements at the different spots, right? And they're not going to give that to you. Now, to further mitigate the effects of cross-hybridization, you could also use two sets of probes, right? One of them is called a perfect match probe or PM probes. These are the ones designed to perfectly match selected nucleotide sequences in the target mRNA, right? Whereas you could also have mismatch probes, all right, where you go and change one of the nucleotides. So mismatch probes are derived from the perfect match probes by changing one base at a central location, right? At some location you go and change it. So if a perfect match probe is aimed at identifying a particular messenger RNA by matching a string of bases in the messenger RNA, then it is more probable that the mRNA will hybridize to the perfect match probe rather than to the mismatch probe derived from it, right? And it is argued, and again, it may not be correct, okay, all these are like kind of ad hoc arguments, hand-waving arguments. So it is argued that subtraction of the intensity for the mismatch probe accomplishes a correction for both background noise and cross-hybridization, right? So again, I mean, some amount of hand-waving, okay, it's not rigorously shown here. So with this in mind, the expression level for a probe set on a microarray can be estimated by the average difference, right? Where you're taking the difference between the perfect match, right, minus the mismatch reading, right, taking the difference between those two and then averaging them out over all the probes where the variation is not too much. So A is the subset of all probes K such that the difference between the perfect match intensity and the mismatch intensity is within 3 standard deviations of the trimmed average of all differences. Okay. The smallest and largest difference being left out of the average, and where this sign, absolute value sign around A, or the cardinality of A, is the number of probes in A. And alterations of this basic average difference have been proposed, and various problems have been pointed out regarding the average difference, including the fact that this MM, the mismatch intensity, could often exceed the perfect match intensity, right? So again, this is all hand waving, right? There are hundreds of papers that have been written on microarrays, but I don't think they really have any new substance or anything like that. If you have time, you want to become an encyclopedia on microarrays, you can go and take a look at them. Right? But most of it is hand waving. Somebody used some method for data analysis or whatever, and somebody else changed it a little bit. They wrote some more papers and so on. Okay, but I don't think that there is any definitive word on the topic. Okay, but the key idea is that each gene is going to hybridize to its complement. Okay, and that's how, by putting the complements of thousands of genes on the same slide, right? You're trying to measure the activity of a large number of genes. You're trying to simultaneously measure the activity of a large number of genes. And today you have, this initial microarray thing that they have in this paper, right? I think that had like 8,000 probes, right? Today, some of these chips, they have the entire human genome on one single chip, right? And with a lot of replicates also, like maybe 44,000 genes or something like that, you can do it on one chip. All right, any questions? So the next chapter that we would move on to, all right, is classification. Okay, but I'm now going to switch from the PowerPoint notes, all right? I'm going to switch to those two files that I sent you, right? Those two PDF files, okay? And I will cover the material in those 2 PDF files, and then once we finish that, then I will go back to classification and continue here. There will be 2 cases like that, like for this analysis of ratio analysis of CDNA microarray images. All right, that's one place where I will deviate from the notes. I'll give additional material which I already sent you, and then the other place is when we talk about gene expression prediction, right? So there also I will discuss another paper, and there is also explanatory material that I will send at that time, right? So let's get out of this for today. Yeah, for today I don't think we will need this anyway. I'll just minimize it so to be on the safe side. Okay, let's go ahead and open the ratio explanation papers, right? Okay, so first, all right. So here in this, so the paper is there. Okay, I'm going to discuss this very shortly, right? But before that, I want to go through the derivation of some of those equations in the paper, right? And some material that you may not be familiar with. Okay, many of you are probably familiar because you've taken courses in statistics and all that, So, but some of you may not. So I'm just going to go through that material so that when we look at the paper, right, we know right away what is being done. Yes, go ahead. I think so. I did send 2 PDFs, right? I mean, didn't I? Yeah, I did send on Friday. I sent it out. Oh, did you guys get chapter 15? Oh, okay. Then I need to send it. I sent you the wrong one then. Chapter 15, was it about CODs or what? Oh, okay. No, then I will send this. Okay, I will send this after the class. Okay, unintentionally I mailed the wrong file, but that's okay. Hold on to this. We are going to need the chapter 15 later on. Okay. So here we are going to cover a number of things. All right. So the first one, so in this particular paper, that is 1997 paper, ratio-based decisions on the quantitative analysis of CDNA microarray images, right? We will need a number of results, okay? And I want to fill in some of those details. The first one in question is what is called the Mann-Whitney test or the rank sum test, right? So here you're interested in comparing 2 populations, okay? Whether they have the same means or not, okay? They have similar means or not. So how do you check that? So you basically draw samples from each of the, so let one of the populations be X, all right? Another one be Y, okay? And you don't know anything about the distribution, right? So you draw samples from X, all right? Let's say X1, X2 up to Xn, independent samples arising from X. You similarly draw independent samples arising from Y, Y1, Y2 up to Ym, right? The samples do not have to be of the same size, okay? You can draw M from one, N from the other. And these are numbers, okay? So now you're going to arrange them, right, in ascending order of magnitude, okay? And then for each entry, right, so you might have x1, y1, x2, x3, y2, and so on, okay? Now for each of these guys, okay, you're going to assign a rank. Like you've arranged them in ascending order of magnitude. For each of these variables, there is a rank, okay? If it's the first one is rank is 1, second one is rank is 2, and so on, okay? Then you're going to go ahead and sum all the ranks over the x's, okay? For each of the x's that appear in that order, right, take the rank and then add all of them together, okay? That is called the rank sum statistic, right? And you can check that against some value to determine. So under the assumption that x and y have the same means, if x and y are really have the same means, okay, then probably that rank sum statistic should have a lower bound and an upper bound, okay? If it lies outside, right, then probably they don't have the same mean, okay? That's the test that is done. So I'm going to try to at least give you an intuitive feel for that. So under the null hypothesis is that x and y, right, just 1 minute, let me just read this a little bit. Yeah, this is better. So, yeah, this is better, yeah. So you've gone ahead and arranged them in ascending order of magnitude, right? And now you're going to add together all the ranks associated with the x's, okay? So that is called the rank sum statistic, right? So Rxi is the rank of Xi in the above ordering. Now clearly, all right, see you can have two extreme situations, okay? The X's might be significantly smaller than the Y's, all right? Then it is very likely that when you sample all the X's, X1, X2 up to Xn, they are occurring before any of the Y's, okay? So in that case, this statistic, so you can say that the minimum value of this statistic will be when all the X's occur before any of the Y's, okay? And in that case, if you sum up the ranks of the individual X's, you will get 1 plus 2 all the way up to n, right? And you know that this is n times n plus 1 over 2. That's the minimum value. The other extreme scenario will be when all the Y's, okay, occur before any of the X's, right? So that means the X's will now start out, the ranks will start at n plus 1, right? And go all the way up to n plus n, right? And in this case, the sum will be the sum of the first n plus n natural numbers, that's n plus n plus 1 over 2, right? Minus the sum of the first m natural numbers, which you are missing here, okay? So minus m plus 1 over 2. So you can put certain bounds on this, okay? Furthermore, you can go and calculate the mean of this rank sum statistic, okay? You can calculate the mean because you're assuming that both of them are coming from the same from a population with similar means, okay? So because of that, every time you draw, right? So each one is equally likely to occupy a particular position, right? So let me just go to the next slide, and I think you'll be able to follow the argument better, right? So we can show that under the null hypothesis means the two populations have the same mean. So the mean of X is equal to the mean of Y. You can show that the expected value of this rank sum statistic is n times n plus 1 over 2, right? And the variance of this rank sum statistic is nm n plus m plus 1 over 12, all right? So let me show you this one, okay, because this one is easier to show. How do you arrive at that? Well, the expected value of W is going to be the expected value of the rank sum statistic. Well, that is the sum of all the ranks of the individual Xi's, right? But you can bring the expectation inside the summation sign, right? No problem. But now look at this, okay? You know that this rank of Xi, okay, what values can it take? It can take values 1, 2, 3, 4 up to m plus n, all right? And if the two populations have the same means, all right, then the assumption is that it can take any of these values, all right, with equal probability, right? So that's why what you can do is it's going to take the value 1 with probability 1 over n plus m. 2 with probability 1 over n plus m, 3 with probability 1 over n plus m, all right, equally likely events, n plus m equally likely events. So you go ahead and add these guys together, okay, these are the ranks, all right, equally likely. Now, again, I mean, this is 1 plus 2 plus 3 up to n plus m, right? So this is, again, using that formula n plus m times n plus m plus 1 over 2, right? The n plus m's cancel out. You're left with n plus m plus 1 over 2, but the summation variable is I, all right? So there will be actually n of these guys, okay? So you can pull this fellow out, multiply this by n, right? That's the result that you got, and that's what I have here, right? So you can calculate the expectation. You can also show that the variance is this, okay? And again, I mean, you guys are, you know, bigger experts than me at 303, all the random processes and all that, so you can go and show that, okay? So it can be shown that the expected value is this and the variance is this, all right? So now you can construct a table of values of this statistic W, right? And this is a function of alpha, n and m. N and m are the two sample sizes, right? And if you look at a book on statistics, they will have these rank sum tables, right, at the back. So the test will be the following, right? So you will calculate the rank sum statistic from your data, right? If the value that you calculate exceeds whatever value is given in that table, right, for that level of confidence alpha, for the sample sizes n and m, then you're going to reject the null hypothesis. Then you're going to say that the two don't have equal means, okay? If it doesn't exceed, then you cannot reject the null hypothesis, right? And for n and m greater than or equal to 8, this statistic, right, where you're taking the rank sum statistic minus the mean of the rank sum statistic divided by its standard deviation, that approximates a standard normal distribution, right? And why are we using this? Because this doesn't require any assumptions about distribution. This rank sum statistic, right? This is a distribution-free test, right? We don't know whether it's normally distributed or not. So that's the reason why this is being used. Right? So this is one thing that is going to be used in the paper. And where is it going to be used? You need to figure out, okay, at each of the microarray spots, right? You need to be able to figure out which one is the background, right? And which one is the signal, right? There's a target patch, right? There's background outside, okay? Because see, the robot is going and putting it over there, but every time the robot moves, right, it might be at a slightly different location. So looking at these intensities, can you differentiate between the background and the actual signal, right? And the way you will do that is there will be two populations here. You will say that the background has got low intensity, right? So you will say that the mean of the signal is significantly higher than the background, right? So you make the rank sum assumption that test assumption that they have the same this thing, and then you will reject the null hypothesis, right? You'll throw points out, and then I'll show you how that is done, okay, when I get to the paper, right? But this is one tool that you're going to need, right? So that's why I covered this first. Right? All right, any questions? All right, now the next thing that I want to talk about is what is called the Chebyshev inequality, right? So which you're probably familiar with, right? Does everybody know about it, or otherwise we can do a quick proof of that, right? Can anybody do a quick proof of that? I think you guys should be able to, because I'm not a stochastic person. You know, if I can do it, you guys should be able to do it, right? A quick proof of the Chebyshev inequality, all right? Yeah, let me do that, okay? Let me do that. Maybe I'll get stuck, then we'll quit or something, but let's just, minimize this window and let me do the quick proof of the Chebyshev inequality. Then that'll make more sense, all right? So let's just, okay, now I'm going to, okay. Okay, so let's try to do a quick proof of the Chebyshev inequality, right? So this is October. Oops. What happened? Why isn't this working? Right? I thought. I need to change the left thing to what? To the pen? Which pen? Okay, the black pen. Let me see if it'll work. No, it still doesn't work. Huh. What? Yeah, can you? No, I want to record it. So that I don't have to teach the class the next time. So it should be working. In the other class, it works all the time. So the pen is not working? Oh, okay. Let's try the other pen. Maybe the yellow pen might work, No, it's not.
The touch screen has some problems, so it doesn't work. It doesn't recognize the touch of the screen.
Yeah, let's try to do it if it works, It's really weird because in the other class I'm using that every day, so it works. So is this thing plugged in or? Probably it is. Okay, I guess we'll have to do without the proof of the Chebyshev inequality. So that's okay. All of you know that. Okay, so you'll open some book and take a look at the proof. Right. All right, let's go here. Okay, so we will talk about the Chebyshev inequality without proof. All right. So, so the probability, right? That if you have a random variable x, right, the difference between x and its mean, right, the probability that exceeds the quantity epsilon, right, is less than the variance of the random variable x divided by the square of epsilon. Okay, so just accept this on good faith. If you don't believe it, if you don't believe me, I can show it to you, but it's not my fault. Okay, this thing is not working, right? The screen is not working over there. So from this you can see that if epsilon is greater than 3 times the standard deviation, right, then the probability that, so this is the difference between x and its mean is greater than epsilon, okay. So that means the probability that x minus its mean is less than equal to epsilon will be 1 minus this quantity, right. So from here you can see that the probability that x lies between mu x minus epsilon to mu x plus epsilon, right, is actually greater than or equal to 1 minus 1/9, because if epsilon is greater than 3 times sigma x, right, you plug in the numbers here, 3 squared is 9, so you get 1 minus 1/9, that is 8 over 9, right. So that's pretty high, right. So, and this is independent of any distributions, okay. If you make distributional assumptions, you'll be able to do better, okay. So independent of any distribution, you can see that within 3 standard deviations of the mean, right, you are going to have almost 90% of the probability mass, right. So for normal random variables, you can get even better Browns. Okay, so one of the items we need when we are going to introduce hypothesis testing is basically the Chebyshev inequality, right? Another thing that we will need is the fact that the sample mean, right? When you calculate the sample mean, right? Pardon me. Now, when you calculate the sample mean, right? The sample mean is basically the expected value of that is the same as the mean of the original random variable, right? But the variance of that is the variance of the original random variable divided by n. Okay, that's the reason why we take averages. Okay, when instead of taking one reading, you take several readings and you average. Okay, because you're trying to bring down the variance. Right. So if x is a random variable with mean mu x and variance sigma x squared, then the sample mean x bar, which is 1 over n sigma I going from 1 to n xi, where xi are independent samples of x, has the same mean mu, but variance is sigma x squared over n. Right. So you can now apply the Chebyshev inequality to the sample mean. Right? So if you do that, right, now the sample mean has got the same mean, right, as the original random variable. So you get probability that x bar, the sample mean minus mu x, the original mean is greater than or equal to epsilon, is less than or equal to sigma x square, right? But now the variance is sigma x square over n, right? So n times epsilon square. So you can see that by making n large, right, you can make this probability as small as you want. Yeah. So with the result that the probability that the sample mean, right, will lie within a distance epsilon, right, of the actual mean, right, the population mean, that can be made as close to 1 as desired, right, just by cranking up n. Okay, if you have a large enough sample size. Okay. Now, the way you'll do the hypothesis testing is, so okay, that the sample mean must lie like x bar, right? The sample mean should lie between mu x minus epsilon and mu x plus epsilon with a certain probability, right? And this probability will approach 1. Yes, sir. Go ahead.
How do you get to know the mu x?
No, you don't need to know mu x. Okay. The way when you do the testing, right? No, see, you'll make an assumption like mu x equal to some value, let's say, okay? Let's say you make an assumption, okay? Now, you make an assumption that the mean population mean is something, okay? Now, if you take samples, right, and then you calculate the sample mean from the samples, okay? If that deviates too much from the mean that you assume, that means your mean is wrong, right?
It's kind of an iterative process. So if you find that it's far from the mean you assume.
No, you usually in a lot of situations you are comparing the difference between two means, okay? So if the two means are equal, right, then the difference would be 0, okay? Something like that, okay? Like, let's say you are contesting an election, okay, and she's contesting the same election, okay? We want to figure out who's going to win, okay? So we say, okay, they have equal chance of winning, both of them. Then the mean is 0, okay, of the difference, right? And then we'll take samples. We will ask people, okay, whom are you going to vote for, okay? And based on that, on the size of the population that we sample, we can say with this much of confidence, okay, that you're going to win versus her or something like that. So that's what they do when they report it on the news, okay, with the poll. It has the margin of error this much. That's what is being done, okay. Nothing more, nothing less, all right. So pretty straightforward statistics, right? And of course, if you're starting from the Chebyshev inequality, you're not making any distributional assumptions, okay? If you know that something is normally distributed, okay, like if you have like the law of large numbers or the central limit theorem, okay, where when you take the normalized random variable, right, as you let the when you take the mean of a large number of random variables, right, it's going to become normal, right? So then you can use the normal distribution tables, okay, from the back of your statistics book, and then figure out what is the degree of confidence. Yeah. All right. Any other questions? And again, this stuff is important. It's not just for this course. Okay. I'm covering it because if you don't know this, then in the paper he assumes you know all of this stuff. Okay. The authors assume that it's like ABCD. All right. But then if you don't know this stuff, then you'll have trouble following the paper. Right. Any other questions? So based on what I showed you, right, a few minutes ago, you can see that as the sample size goes to infinity, the sample mean is going to go to the population mean, right? Right? And this is the basis for the hypothesis testing, right? So suppose you have a random variable x with mean mu, right? We want to test the two competing hypotheses, right? The null hypothesis, and mu zero is that value that you are talking about, right? The null hypothesis is that the mean is a particular value mu zero, and the alternative hypothesis h1, right, is that mu is different from mu zero, right? And suppose the variance sigma square of x is known. If sigma square is not known, there is a way to calculate that, okay? That's where they use the t statistic, right? They will not use the z statistic, yeah. The t-test, okay, that's the famous t-test, right? Because look, like we submit proposals, let's say to NIH or something, our proposals will get shot down, okay? Because, we are going to talk about like solving the whole problem, holistic view and all that. Typically what they do, what they are interested in, okay, I mean, I've seen a lot of those proposals. It's like you're going to say that drug A is going to perform better than drug B, right? And how do you do that? You run some tests, or give drug A to some people, drug B to some people, and then with those numbers, all right, you do a comparison t-test, okay? Because in this case, you do not have sigma, okay? So you have to estimate that sigma, and the statistic that is appropriate to use in that case is the t-statistic. And there are tables of t-statistics at the back of the book. So you do, no, it's not cheating because you cannot compute all of those, right? I mean, you probably could, but you're not interested in the theory. You just want to look at the table and then see if your number exceeded, okay, then you will go and say, okay, yeah, they're different, okay, one is more effective, and they talk about p-values and things like that, okay. So if you're going to be working in this area, you might want to, learn more about p-values and hypothesis testing and all that, because that's what the biologists also seem to understand, okay. They like to know what the p-value is, and, but that's the probability of making, roughly the probability of making a mistake, all right. So they want to know that, right. So in hypothesis, so suppose that the variance sigma square of x is known, just to keep things simple, right? Then under the null hypothesis, that is, the mean is actually mu zero, right? For a given significance level alpha, you can determine, right, this z1 alpha over 2, because see, in the limit, okay, if you're taking the sample mean, in the limit, it will be a normal distribution, right? If you're taking the sample mean, right, I mean, like, it's going to be a standard normal if you take out the mean and make the variance unity, okay, by appropriate scaling, it'll become a standard normal, okay. So then you can use the table. If you want to have, only 5% in the tails, okay, the normal is symmetrically distributed. So you put 2.5% here, 2.5% here, calculate those two values, okay. So you can say, okay, with 95% confidence that the mean is going to lie in there, right. So suppose the variance sigma square of x is known, then under the null hypothesis for a given significance level alpha, we can determine these two values from the standard normal distribution such that the probability that the sample mean, x bar, right? This is actually more than that. It's the sample mean that has been normalized, okay? Right? So the the probability that this variable, right, lies between these two limits is 1 minus alpha, okay? And alpha could be like 0.05 or something like that, okay? So then the probability that the sample mean lies within these two limits, okay, is like 95%, right? Now, if you actually calculate the sample mean and it doesn't lie between that z1 alpha over 2 and z2 alpha over 2, right? What does that mean, okay? That means something is wrong, right? I mean, that means your assumption is wrong. So that's when you would reject the null hypothesis, right? So if the value of the test statistic falls outside this interval, then you will reject the null hypothesis with a level of confidence 1 minus alpha with 95% confidence. So that's what is typically done in hypothesis testing, right? And we need to do that because remember here we are trying to compare whether that ratio is going to be 1 or not, okay? Again, I mean, you need the probability density function because based on that you can construct, you can go ahead and construct the interval, right? Confidence interval. You want to have 95% confidence, right? That it is different from 1, okay? then you wouldn't go too close to 1. Okay, you'll stay a little bit away from 1 on each side, right? And you'll get your 95% confidence interval, right? So that's why you have to calculate that C. C is the parameter that is appearing in the probability density function. It's not normally distributed, it's some other distribution, but you have to calculate all those quantities, right? So this is about hypothesis testing, right? Okay, any questions so far? Okay, this here is basically the derivation of a particular equation in the paper. Okay, as we go through the paper, later on you can look at this. There's an equation 6 in the paper where they come up with the probability density function for the ratio, right? And then you have to go and perform all these integrals and all that to come up with the next equation that is used in the paper. Because you're making some assumptions as you go along, right? To get some a nice expression for carrying out the calculations, right? So this is the final probability density expression containing C that you get, right? So we can come back to this after we have discussed the paper, right? The other thing I want to cover is the maximum likelihood estimation, right? And again, this is a topic that will be covered in some of the I don't know, maybe the grad courses, right? Here they should be covering, yeah. So and the idea is the following, right? So suppose x is a random variable with density function f of x and theta, right? So the density depends on some parameter theta. Like if it's a normal distribution, theta could be the mean and the variance, right? And theta is an unknown parameter which appears in the density function. So suppose, based on this probability density function, you are getting samples, all right, x1, x2 up to xn. These are independent samples or measurements that you're getting for that function, all right, obtained from x. Then x1 through xn are independent, identically distributed random variables, and the joint density function will be the product of the individual densities, right? So the joint density function, f of x1, x2 up to xn, right, and theta is also called the likelihood function, right? And it represents the probability that you're simultaneously going to have the random variable x1 equal to little x1, x2 equal to little x2, x3 equal to little x3, and so on for a given theta, right? So then, so the likelihood function is the probability that x1 is x1, x2 is x2, xn is xn for that given theta, right? So it would make sense because if you observe, right, if you take measurements of capital X1, X2 up to Xn, right, and you observe these values little x1, little x2 and up to little xn, okay, that's what you actually saw, okay. It would make sense for you to try to select theta to maximize the probability, all right, of seeing what you actually saw, right. That's the idea behind the maximum likelihood estimation, right. So thus it makes sense to choose theta to maximize this probability. The value of theta that does that is called the maximum likelihood estimate. And again, I mean, many times, you can just take the log because the function stays the same, all right? It's a monotonic function. So since the log is a monotonically increasing function, sometimes for ease of computation, one chooses theta to maximize the log of the likelihood function, right? And that's what is typically done. So in this paper, right, we calculated a density, right? So from that density function, we can go ahead and calculate the maximum likelihood estimate. And that's what gave you that C hat expression that I had on the earlier slide. Okay, we will go through the paper next time. I will point out these equations, all right, as we go, right? Oh, one more thing, okay. Or maybe I'll do that next time. When you have a random variable y, which is a times x, all right, how do you relate the density of y to the density of x, all right? So I'll probably do that next time. I think we are running out of time, so yeah, let me continue from here next time, and next time we'll finish the discussion of the paper also completely, okay? We may not have any class on Friday, right? I'll let you know on Wednesday, okay? Because there's a group that is coming to tour the center, and I think we have already made good progress, so I might just go there to talk to them, so. But I'll let you know on Wednesday, whether I will do that. But we should be in good shape because once we finish this on Wednesday, then we'll move on to classification, clustering, expression prediction, modeling, and control. Okay. Any questions?